In today's interconnected digital landscape, systems rarely operate in isolation. The ability to integrate different components, services, and applications has become the cornerstone of scalable, maintainable software architecture. This comprehensive overview explores 9 fundamental integration patterns that form the backbone of modern enterprise and cloud-native applications. 1. Peer-to-peer, P2P, decentralized communication. The democratic network model peer-to-peer integration represents one of the most fundamental yet powerful architectural patterns. In this model, multiple systems communicate directly with each other without requiring a central coordinator or intermediary. Each node in the network acts as both a client and a server, creating a truly distributed system. How it works? Order services, user management systems, inventory trackers, and notification services all maintain direct communication channels with each other. When an order is placed, the order service can directly notify the inventory system, which can then communicate with the user service to update customer information, while simultaneously triggering the notification service to alert relevant parties. Key advantages: resilience, no single point of failure since there's no central coordinator; scalability, new nodes can join the network without requiring central reconfiguration; efficiency, direct communication reduces latency and eliminates bottlenecks; autonomy, each service can operate independently and make local decisions. Common use cases: microservices architectures with service mesh implementations, blockchain and distributed ledger systems, content distribution network CDNs, file sharing, collaborative systems. 2. API Gateway, the central traffic controller. The central traffic director, an API gateway, serves as the single entry point for all external client requests, acting as a sophisticated traffic director that routes requests to appropriate backend services while providing essential cross-cutting functionality. Architectural intelligence: the gateway analyzes incoming requests and intelligently routes them to the correct backend services, whether that's Service 1, Service 2, or Service 3. This pattern is particularly valuable in microservices architectures where a single user action might require coordination between multiple backend services. Core capabilities: request routing, directs traffic based on URL patterns, headers, or other request characteristics; authentication and authorization, validates credentials before requests reach backend services; rate limiting, controls traffic flow to prevent system overload; request and response transformation, modifies data formats between clients and services; monitoring and analytics, provides centralized logging and metrics collection. Business value: simplifies client integration by providing a single endpoint, enables independent scaling and deployment of backend services, facilitates API versioning and backward compatibility, provides centralized security enforcement. 3. Pub-sub, publish-subscribe, event-driven architecture. The asynchronous messaging pattern. The publish-subscribe model revolutionizes how systems communicate by introducing asynchronous, event-driven interactions. Instead of direct service-to-service calls, systems publish events to topics and interested services subscribe to receive relevant notifications. This decoupling allows systems to evolve independently while maintaining loose coupling. Core components: publishers, services that generate and broadcast events; subscribers, services that consume and react to events; topics or channels, logical groupings of related events; message broker, infrastructure that manages event routing and delivery. Benefits: loose coupling, publishers don't need to know about subscribers; scalability, new subscribers can be added without modifying publishers; reliability, message brokers can provide durability and guaranteed delivery; real-time processing, enables near instantaneous event processing. 4. Request response, the classic synchronous pattern. The traditional communication model, request response, represents the most intuitive integration pattern, mirroring how humans naturally communicate. A client sends a request to a service and waits for response before proceeding. The synchronous flow: the client formulates a request containing the necessary parameters and data, sends it to the target service, and then blocks, waits until receiving a response. The service processes the request, performs the necessary operations, and returns a response containing the results or an error message. Characteristics: synchronous, client waits for response before continuing. Bidirectional, information flows both ways. Immediate, results are available immediately upon completion. Simple, easy to understand and implement. When to use: operations requiring immediate confirmation, critical business transactions, interactive user interfaces, simple CRUD operations. Considerations: can create tight coupling between services. Blocking nature can impact performance, requires careful timeout and error handling, may not scale well under high load. 5. Event sourcing, the complete history pattern. Capturing every change, event sourcing fundamentally changes how we think about data storage. Instead of storing current state, systems store a complete sequence of events that led to the current state. This creates an immutable audit trail and enables powerful analytical capabilities. The event-driven data model: every change to application state is captured as an event. These events are stored in an append-only event store, creating a complete history of everything that has happened in the system. Current state can be derived by replaying events from the beginning. Core concepts: events, immutable records of state changes; event store, database optimized for storing and querying events; event handlers, components that process events and update read models; snapshots, periodic state captures to optimize replay performance; powerful capabilities, complete audit trail, every change is permanently recorded; time travel, system state can be reconstructed at any point in time; event replay, new features can be built by processing historical events; CQRS integration separates command and query responsibilities. 6. ETL, extract, transform, load, the data integration workhorse. The data pipeline foundation: ETL processes form the backbone of data integration in modern organizations. This pattern involves extracting data from source systems, transforming it into the desired format, and loading it into target systems for analysis or operational use. The 3-stage process: extract, data is pulled from various source systems, databases, APIs, files, or streaming sources. This stage must handle different data formats, connection protocols, and access patterns. Transform, raw data is cleaned, validated, enriched, and transformed into the target format. This might involve data type conversions, field mapping, aggregations, or complex business logic applications. Load, process data is written to the destination system, whether that's a data warehouse, operational database, or analytics platform. Modern variations: ELT, load raw data first, then transform, better for cloud environments. Streaming ETL, real-time data processing for immediate insights. Microbatch, small frequent batches for near real-time processing. 8. Batching, the efficiency optimizer. Processing at scale: batching addresses the challenge of processing large volumes of data or operations efficiently. Instead of handling requests individually, the system collects multiple operations and processes them as a group. The accumulation and processing cycle requests or data items are collected over a specific time period or until a certain volume threshold is reached. Once the batch criteria are met, all accumulated items are processed together, often leveraging economies of scale and optimized algorithms. Benefits: efficiency, reduced overhead per operation; throughput, higher overall processing capacity; resource optimization, better utilization of system resources; cost reduction, lower per operation costs, especially in cloud environments; trade-offs: latency, individual operations experience delayed processing; complexity, requires batch management and monitoring; error handling, failed batches affect multiple operations. 9. Streaming processing, real-time data in motion. The continuous flow model. Streaming processing treats data as a continuous flow rather than discrete batches. This enables real-time analytics, immediate responses to events, and the ability to act on data as it arrives. The continuous pipeline. Data streams continuously through processing pipelines where it's filtered, transformed, aggregated, and analyzed in real time. Results are immediately available for downstream systems or user interfaces. Key characteristics: low latency, sub-second to millisecond processing times, continuous. Processing never stops, data flows continuously. Scalable, can handle massive data volumes to parallel processing. Stateful, can maintain context and state across events. Use cases: real-time fraud detection, live analytics dashboards, IoT sensor data processing, financial trading systems, social media monitoring. 9. Orchestration, the workflow conductor. Coordinating complex business processes. Orchestration manages complex business processes that span multiple services and systems. A central orchestrator coordinates the execution of various steps, ensuring proper sequencing, error handling, and compensation actions. The central coordination model. The orchestrator maintains a workflow definition that specifies the sequence of operations, decision points, and error handling procedures. It coordinates calls to various services, service A, service B, service C, ensuring that the overall business process completes successfully. Orchestration capabilities. Workflow management defines and executes complex business processes. Error handling implements retry logic and compensation actions. State management tracks process state across long-running operations. Monitoring provides visibility into process execution and performance. Versus choreography. While orchestration uses central coordination, choreography allows services to coordinate through events without a central controller. Both patterns have their place in modern architectures. Choosing the right integration pattern. Decision factors. The choice of integration pattern depends on several key factors: performance requirements, low latency streaming processing or direct API calls, high throughput batching or asynchronous messaging, real-time pub/sub or streaming processing. Consistency needs: strong consistency, request response orchestration, eventual consistency, event sourcing or pub/sub. Audit requirements: event sourcing for complete traceability. Scalability demands: horizontal scaling, peer-to-peer or pub/sub, vertical scaling, request response with load balancing, elastic scaling, API gateway with microservices. Modern architecture combinations, hybrid approaches. Real-world systems typically combine multiple integration patterns. CQRS plus event sourcing, separate command and query models with complete event history. API gateway plus pub/sub, external API management with internal event-driven architecture. Streaming plus batching, real-time processing with periodic batch reconciliation. Orchestration plus choreography, central coordination for critical processes, events for loose coupling. The future of system integration. These 9 patterns represent the current state-of-the-art in system integration, but the field continues to evolve. Emerging trends include event mesh, global event distribution across hybrid and multi-cloud environments, function as a service (FaaS), serverless integration patterns, AI-driven integration, machine learning for intelligent routing and transformation, graph-based integration, knowledge graphs for semantic integration. Understanding these fundamental patterns provides the foundation for designing robust, scalable, and maintainable distributed systems. Each pattern addresses specific challenges and offers unique benefits, and the art of system design lies in selecting and combining the right patterns for your specific requirements.